Thank you for the opportunity to share with you a little bit of what we've been doing. I'm actually involved in 3 projects on Blue Waters. We use it quite a lot. The other 2 are going to be on Thursday, so if you want to know some more details about some other projects. But today, I'm just going to talk about the unconventional superconductors that we've been working on by doing many-body quantum simulations. And you might say superconductors, well, that's maybe not that interesting to people who aren't physicists, but actually they are. This is actually from CERN. Of course, this is a physics application. But they have to run these big currents to run the magnetic fields. The same technology is used in MRI machines for medical purposes. And for 12,000 amperes, you need this much copper, right? And for the same amount, you need this much of a superconductor, right? So it's a huge difference. And so if you're thinking about in New York, trying to get your power lines through these small conduits now, they're starting to put in superconducting conduits. So this is actually an important thing for our energy and that sort of thing as well. But superconductors also have really interesting new things, which apparently unique properties, which is, I got a little too excited. Okay. So this is something you can do with a superconductor that you cannot do with any other material, so that you can do the levitation, right? You have stable levitation over magnets, which is impossible without a superconductor. And these guys show how you can make these really fun devices where they do a little Hot Wheels track here, and it's just flying around without any, yeah. It's pretty cool, right? And this thing just flies around. And if you ever get a chance, look up Stephen Colbert. He floated a Ben and Jerry's ice cream container around on a track just like this. So you can do these really nice friction-free things with that. And so if you think about it, I mean, this is really great because it's a type of material, it's a type of device which has very unique properties. And when that becomes available to people who are working technology, that's really important. However, it's not very available because you see how this is trailing smoke? That's, of course, water vapor because it's cooled by liquid nitrogen before you put it on there. It has to be very cold. And that's an issue. Okay, so what is this thing? By the way, I said liquid nitrogen. That was a huge advance in 1986 that we did it with liquid nitrogen. It used to be liquid helium. And the huge advance was this guy here. This is actually part of a class of materials called the cuprates. They were discovered to be superconducting in 1986. They were sitting on shelves for many years before that. People didn't know about them. And basically the way they work is this. This is the atomic structure, and you have copper oxide planes. This is copper and this is oxygen. And then you have lanthanum oxide kind of spacers, right? And so what you do, if you just make it like this, it's people call it an antiferromagnetic insulator. Basically, it's a boring ceramic material. It doesn't do that much electronically. But as you put in strontium atoms for the lanthanum, you dope it. And as you dope it, what happens is it becomes metallic, and it becomes a superconductor. And this is actually up to 150 Kelvin, which is pretty high for superconductivity, considering previously the maximum was about 30. Right, so it's a big difference. We're about halfway where we want to be. We want to be at 300. So we have a long ways to go, but that was a huge advance. Now, we actually don't understand how this works. And just to explain to you a little bit about what I mean by that, if you think about a low TC, like a low temperature superconductor, this is a piece of lead. It gets superconducting around 6 or 7 Kelvin. We actually understand very well how this works. The way this works is that you have an electron is flying by, and this is how we draw this in physics. It's flying around, and then it somehow interacts with the lattice of the nuclei. That sends a vibration over to another electron, which causes it to interact. And so these electrons are actually interacting through the lattice vibrations. And that actually makes, you can work this out, and it makes an effective attractive interaction between the electrons. I'm not going to go into details exactly how that creates the superconducting state, but once we get there, we understand it, right? So we say attractive interaction, we get a superconducting state. Now, in the high TC ones, the ones with the maximum observed temperature of 150 Kelvin, this is the maximum theoretical temperature. So given this mechanism, this is how high you can go. We observe this. So already you say there's something different about this, right? 150 is a lot bigger than 30. So electron lattice interactions are not enough. And we don't know really exactly how they work. but there's the possibility that there's an emergent state from electron-electron interactions. So directly electron-electron interactions are creating this emergent state. Now, I just told you that we needed an attractive interaction. As hopefully you learned in Physics 212, when you took it here in Illinois, which I just finished teaching, electrons are both negatively charged. Two negatively charged objects repel each other, right? So that doesn't seem like that should work. This is why it's a mystery. We don't understand exactly how this comes about. If you just try to compute, if you say, I'm going to do electronic structure calculation, standard electronic structure calculation, which is done all the time. It's so standard you can go to materialsprojects.org, and they have electronic structure calculations for every single material that's known to man on this website with the standard stuff. Now, if you look up lanthanum copper oxide, which I just showed you, I told you it's an antiferromagnetic insulator. And this a functional theory, which is this current standard, it's calculated as being non-magnetic, no gap, which means that it's not an insulator. And actually, it's not even stable, so it wouldn't even exist. So there's some serious failures there. And the reason is that we're not actually able to solve the quantum mechanics well enough. So we need better simulations to predict these properties. And what we really need to do, we need to go back to the basics, right? And the basics is just a Schrodinger equation. Now, some of you may or may not have done quantum mechanics, I understand that. But you can think about it this way. This is really just a very high-dimensional partial differential equation that we have to solve. And what we were looking for is this wave function here, which is basically going to tell us the probability of finding electrons at given places. The square of that is the probability. And it obeys this equation. And this is just a linear differential operator here, this H. We're going to call it Hamiltonian. It's something that tells you the energy of the system. Superconductivity is actually really exciting because, of course, it's a macroscopic quantum phenomenon. But this same equation, the same quantum mechanics, describes so many other things, like nanofluidics, which is going to, Yan-Bin there is going to talk about on Thursday. DNA molecules actually are there. Solar cells, Professor Artikin there is going to talk about it on Thursday as well. And these things are also not very well described by the standard solutions. And we need to do better. Okay. So why is this difficult? Remember, we have this differential equation. And this is for every single electron. Remember that in a given piece of material, we have 10 to the 23 electrons or so. That's a lot. So we assume that pieces of it, of course. But we have a very, very high dimensional partial differential equation we want to solve. Right? This is the stationary one, which is slightly simplified. And this is hard because if we split up this differential operator, we have this part, which is actually a separable part. It means our differential equation is separable. We can make a product wave function, essentially. That's the easy part. But there's this part here where electrons, I remember I told you they repel each other. Right? There's an interaction. And that interacting part actually makes the solution of this equation very, very difficult. What typically people have done is you treat this part, this separable part, exactly, and then you try to add an interacting part in some kind of either ad hoc or approximate way. And so we're actually still kind of somewhat there, but what I'm going to describe to you is the methods that we're using on Blue Waters, which is using Monte Carlo. So basically what we're doing is, remember Monte Carlo, the point of Monte Carlo is that you can work in a very high dimensionality, it doesn't care, and only cares about the variance. So what we're trying to do is you want to take a Monte Carlo process and map that on, map basically the process which solves for the solution of our differential equation, and map that onto a Monte Carlo process, right? And this is called Diffusion Monte Carlo. It was really pioneered by somebody here at Illinois from way back, David Stepperly, who's been quite involved in. So it's kind of an old method, and he really brought it to the forefront back in the 80s. But it's been too difficult to apply to things like real materials until recently, Blue Waters and so on. So basically what this is, you make an isomorphism between a stochastic process and the stationary Schrodinger equation. So you get the solutions to the Schrodinger equation out by performing the stochastic process. Basically, this is more for physicists, but kinetic energy corresponds to diffusion kind of process, and potential energy corresponds to a broken back process. And quantum mechanics is all about balancing kinetic and potential energy. So what happens is you put in some potential. This is a one-dimensional implementation. You put in a guess. This is a terrible, if you know physics, this is a terrible guess for this potential. And then you start out your walkers like this. So they're evenly distributed. and then you put them through the process, and what happens is they die out where the potential is large, and they rebirth where the potential is small, and then you get the solution there. And so that's the bend up solution there. Now, if we started out too tight here, then it does the same thing, but it just diffuses out to get to they get to the same solution no matter what. Right? So that's basically how that works. There's one small problem, which is a little bit of a detail, but I think important for those who understand quantum mechanics. They say, wait a minute, Walkers are positive, and electrons are what's called fermions. That means that the wave function actually has positive and negative parts to it. When you switch the positions to electrons, the wave function has to have a negative sign, which is a weird quantum thing, which I'm happy to talk about at length if you're interested and don't know about it. But we need to have positive and negative Walkers for fermionic solution. So this is where our bit one approximation comes in, which is called the fixed node diffusion Monte Carlo. We put in a 0 here, and then the signs of the Walkers are actually determined by the Trout function, and then you run. And if you know well your quantum mechanics, you'll know that this is actually the first excited state of this thing. So if you imagine we got the lowest eigenfunction, and putting this 0 in gives us actually the second highest eigenfunction, right? So that actually allows us to treat excited states and to treat fermions, which are electrons. So when you actually implement this, I just showed you a one-dimensional implementation. The Walkers are actually moving in 3 times the number of electrons dimensional space. This is 1 point in our calculation. So all these little dots here are the points, positions of electrons. This is a path. Each kind of string of little dots is a path of the electrons, and these, what is that, yellow and red spots are the nuclei. Position of the nuclei. So this is kind of one representation. This is one sample, in some sense, of our calculation. So it's a very high-dimensional problem, and we just have a bunch of Walkers. So what I've been doing, a big part of my work has been implementing this into code and applying it to difficult materials. And so we have a open source code that's been around for about 10 years now. And basically, you put in only the atomic positions and the fundamental constants, things like the electric charge and the mass of the electron and that sort of thing. And then we have this stack, which I'm not going to go into detail. I'm happy to talk about more clearly, which is mostly implemented in this open source code here, which you can download. And I'm happy to work with anybody who's interested in it. This is on Blue Waters. We've actually gone up to more than this. I forgot to extend this graph. We got up to 40,000, and it's scaling quite well compared to ideal, which is the red. I think we've improved that a little bit too. And the point is that we just have a bunch of Walkers, so we just spew them all out, and we're going up to 90,000 cores or so. Here is kind of the validation. These are the traditional methods that I talked about before. And here are our results there. So these are a lot of difficult materials here. This is the gap. So this is basically the electronic gap. So we're able to calculate the electronic gap very well versus experiment. Okay, so back to superconductors, which I have a little bit of time to talk about. So again, we calculate various things. We kind of dial in electronic states to look at and calculate their energy and various things. So for example, we can calculate, if you imagine that these are copper here, copper, and oxygen's in between. This is the spin density, right? So electrons have up or down spin. So basically, these are magnetic moments on the atoms. And so this is magnetic moment pointing up, magnetic moment pointing down, right? So they're magnetic materials. And we can look at the energy it costs to flip these guys to all being down, right? That's an important parameter in the theory of these materials. We can also look at things like photon frequency. This is the energy it takes to move atoms around, basically. We can also look at the gap, so the energy it takes to put the electrons up into an excited state. We can look at all these things and compare these experiments for our high TC type materials. Again, the red is the traditional method, the method that most people are trying to use these days or have unsuccessfully used, and the blue is ours. The black is the experimental value. So we're bang on, bang, 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 bang. And this is still written in papers now saying that this is not possible. And we've done that, so that's pretty exciting for me. And this is available in the archive if you're interested. Submit it. So this is really exciting. I mean, it just looks like a bunch of numbers, but for me, it's very exciting because it's been a problem which has been sitting down. Nobody's done this since 1986 when these things were discovered. There's a huge amount of research into this. So then we can go and look at why, and I might skip this because I'm running out of time, but why? But we can go. I just wanted to say we can go and look into why what the traditional theories are actually doing wrong. So we can actually look in very detailed way about the mistakes being made in the literature, because we're able to actually validate our methods here. So basically, there's some details, but I'm not going to go into that. Okay, so then we start to think about what is the origin of superconductivity. We need to start exploring that. We've got a really nice tool now where we think the accuracy is high. So then we start to tackle this very difficult problem of how could it possibly be that the superconducting state emerges at such a higher temperature than what we thought it would be, or what you would think naively. And so most of the approach has been phonons, which are basically lattice vibrations, interacting with charge carriers, right? So it has to be a condensation of the charge carriers. So this is the old version. We know this is not strong enough, right? And then I told you there are magnetic materials. Some people think that magnetism is interacting with the charge carrier. But the problem with that is if you change the isotope, if you change the weight of the atoms, it actually changes superconducting properties. That shouldn't happen with magnetism. So that's a little strange too. So we don't really understand that. So Peter Almonte, who's an experimentalist here, said, well, are these actually independent things? Can we prove that or not, right? And so is there a connection between these things? What is the relationship between structure, like the lattice, the nuclei, positions, and the spin, magnetism? And so he said, are these things coupled? Can we look at that? And we looked at a couple different, so this is, again, the copper oxide planes. These are copper atoms, these are oxygen atoms. And these are two oxygen phonon vibration modes. One is where they're all kind of coming up all at once, right? And the other one is where two of them are going up and two of them are going down. And you have to imagine this is repeated over a large periodic lattice. This guy, when you go into the superconducting state, doesn't shift. It doesn't do anything. You can look at the frequency with Raman spectroscopy. It doesn't do anything. This guy does. They seem really similar, but they do very different things. And it's very hard to test whether or not that interacts with magnetism in the experiment, but we could do it with a computer because now we have this accurate simulations. And so do they change also with magnetic state? And the answer is no here, so no, and yes here. So we think this may have something to do with it. So this is an example of where having the Blue Waters resource allowed us to do a lot of tests and a lot of, you have to remember these are actually very expensive calculations. We're doing this large Monte Carlo in 3,000 dimensions or so. And we're actually able to kind of confirm at least the experiment's intuition about this. And that's this, we haven't solved it, right? But we've gotten some more information about it, a lot more information than we had before. And we're currently using Blue Waters to explore the doping. So just to conclude, so it's allowed us to really make significant progress in one of the most challenging questions in condensed matter physics today. This is not very high on the list in condensed matter physics. And so we now have a technique which can solve the many-body Schrodinger equation at least to sufficient accuracy to make these predictions, to kind of make these things happen. And these initial results actually have been quite useful, and we're kind of happy. We have now this experimental setup we can use to make some really cool predictions. And that's about it. I'd like to thank the College of Engineering for an SRI, NSF, DOE for funding on these projects. Blue Waters, we actually used track time, Illinois time, and friendly user time to do all these calculations. So, we kind of ran the whole gamut there. We also are working with DOE Insight grants and an Exceed grant. The Exceed grant we blew through in about a week. Well, thank you, Exceed, but yeah. And I've done some more work with Narayan Eluru, Elif Artikan, and they're going to be helping on Thursday, and you can get some more information on that. So thank you very much.